Hello and welcome back to our next discussion in chapter 9, and we're going to be talking today about representing a function as a power series. And we're going to return to this idea. Now, it's not something that's unfamiliar to us. We have talked about in 9.7 representing functions as finite polynomials, and then this idea of extending that finite polynomial process indefinitely, and therefore writing a polynomial or writing a function as an infinite polynomial or as a power series using the Taylor polynomial or the Taylor series then. And so, for example, right, we can take a function like e to the x, centered at 0, write it as an infinite polynomial, write it as a power series, represent this function as a power series. But there might be another way to represent a function as a power series, and so we're going to explore that today. We're not going to talk about Taylor polynomials. We're going to talk instead about using geometric series. Now, this doesn't work for all types of functions, like e to the x. I couldn't use a geometric series to get a function or power series out of it. But in certain cases, we can use this method. And so why do I bring up geometric series? Well, let's remind ourselves of what a geometric series is. So a geometric series is a series of the form a sum from 0 to infinity. And we're looking at powers of r, right? So we have a, some constant in front, times r raised to the power of n. And why do I use this series? Because this is the series in which we have a very explicit sum formula. That if the value of r is less than 1, which is going to lead to some restrictions on my representations, if the value of r is less than 1, then this series is equal to a over 1 minus r. A over 1 minus r. Well, why do I bring up geometric series again? Because look at the similarities between a geometric series and a power series. Instead of a constant a, we have some varying constants, an, some sequence constants. Instead of a fixed number r, we have some sort of variable x minus c, still raised to the power n. And so what we're going to be doing today is we're going to be taking the geometric sum formula and thinking of it backwards, is given something that looks like this, rewriting it as an infinite sum, where my r is going to translate to some x minus c term, and my a, well, that's just going to be a constant in general. Might turn into some a sub n at the end, and we'll see how that could happen, but it's just some constant. And so let's look at a very simple example, and let's look at f of x equals 1 over 1 minus x. Wait a minute, that's very explicit. That looks almost exactly like this, where a is 1 and r is x. And so this can be then straight written down as a series from 0 to infinity, a r to the n. So just x to the n. If, well, there are some restrictions. If the value of r, well, r was x. So if the value of x is less than 1. So right away, in one line, we took a function, 1 over 1 minus x, and we wrote it as a power series, as an infinite polynomial, in this case, x to the n. And we can write this function as this power series for all x values less than 1. In terms of an interval, this gives me the interval -1 to 1. So what's the interval of convergence of this power series? -1 to 1. It is very restrictive. Since we're not using the ratio or root test here, remember the geometric says if r is less than 1, its value is less than 1, it converges. Greater than or equal to 1, it diverges. And so actually in this case, we don't need to check endpoints. It's always parentheses. Well, what if, though, we wanted to change some things? So that's great, and we could use this formula directly. But what if I took this function, f of x equals 1 over 1 minus x. But this is a power series centered at 0, right? Just by construction, right? It's a power series centered at 0 using this formula backwards just very directly. What if I wanted this as a power series centered at a different place, say centered at 2? So write f of x as a power series centered at not 0, but 2. Well, in order to get a power series centered at 2, that means we want our r value now, instead of just be x, we need r to be x minus 2. So what do we need? We need my r in the geometric formula to be x minus 2. Some form of x minus 2. Well, it's not right now, right? Why do I need, again, x minus 2? Right? Our r translates to that base of the exponential. And we want a power series centered at 2. And my c being 2 then means that this needs to be x minus 2. So using my geometric formula backwards, we now just need to play a game of algebraic manipulation. I have to change the way the function looks without changing the function. So my first step will be to change the way it looks. And what do I need, right? I change it based on what I need. I need my r. I need this term here instead of x to be x minus 2. Well, that would be great, right? Because then we just use this formula directly to get a power series centered at x minus, or at 2. But remember, this needs to be equal to my original function, right? So we can't just change our expression without paying back any consequences. And so if we look at my original function, it's 1 over 1 minus x. If I look at what I did, I got 1 over 1 minus x plus 2, right? In doing this change, it gave me a plus 2 because of the parentheses with the minus sign. And so because of that, now to balance this out, I need to add 2. That way it doesn't change anything, right? If I simplify this denominator, I get 1 minus x. And therefore I can say equals, that this function is still equal to this function. Okay, well that plus 2, I'll just throw in with that constant in front. I'll make this 3 now. And we're all good. If you simplify this, you'll get 1 over 1 minus x. Well, if I want to use the geometric sum formula, that's great. A over A can be anything. 1 minus r. That 1 is very important. In fact, now it's no longer a 1. By fixing the r problem, making r what I need it to be, I've gotten another problem. Now my 1 is a 3. So again, algebraic manipulation. Now I won't subtract 2 because then I'll just be going in a big circle. And so I'm going to use another trick. I'm going to divide everything by 3. Divide the numerator and denominator by 3. In doing so, of course, I haven't changed anything because everything's divided by 3. I've divided everything. I've multiplied by 1, essentially. Now we get 1/3 there. 1 now minus, and sure, there's now 1/3 in front of the x minus 2, but who cares? It's still x minus 2. And again, if you were to simplify this expression, this is equal to this, which is equal to this, which is equal to this. So I haven't changed the function. I've just changed the way it looks. Why? Because now it's in a form in which I can use my geometric sum formula, where what is A? A is 1/3. What is R? 1/3 x minus 2. And if I write this backwards now, if I go this way, I will get a power series centered at 2 for this function. And so we get that now this function, f of x, is equal to a series. A is 1/3. R is 1/3 x minus 2, then to the n. And typically the way you write power series is just the polynomial term here, x minus c to the n. And so I want to pull this 1/3 out. But of course, in doing so, you need to raise it to the nth power. 1 to the nth doesn't do anything. 3 to the nth we have, and then another 3 gives me 3 to the n plus 1. X minus 2 to the n. And so now you see how we can get a variable kind of term out front based on what my r value is. It has a constant in front, which then gives me some sort of variable term in front as well. And what we just did is we wrote the same function, 1 over 1 minus x, as a power series. Now, it's a different power series, and that's because we centered it at a different place. We did our approximation instead of at 0 at 2. And this is the power series we get if we center our approximation at 2. And this function is equal to this. Not everywhere, this is important, right? The geometric series says, well, this will only work if the value of r is less than 1. And so in this case, if the value of r, which r is a little more complicated now, is less than 1, And so what does that mean about x? Well, if I multiply both sides by 3, we get this. And so this tells me how far away I can move from 2. Remember from the interval convergence and power series, it says 3 units. So we get x minus 2 less than 3 or bigger than negative 3. So that tells me we can go up to 5 and down to negative 1. And so this is a representation on the interval negative 1 to 5. So 1 over 1 minus x, this function is equal to this power series on the interval negative 1 to 5, where this function is equal to this power series on the interval negative 1 to 1. So instead of negative 1 to 1, we have negative 1 to 5. Actually, this interval is a little larger, right? Instead of negative 1 to 1, we get negative 1 to 5, and so this is actually a better one, a better representation to use. And so really the game here, the game of today, is really not really calculus involved. It's more algebraic manipulation. It's given a function, looks something like this, rational, something that can be manipulated in this way. Given a center for my approximation, we need to change the way the function looks without changing the function so that I can use this formula backwards. So I can get it in the form a over 1 minus r, where my r is the right value, and we can write it as an infinite polynomial. And so let's do another one. Let's do f of x equals 1 over x plus 2. And we'll represent f of x as a power series. So represent f of x as a power series. In this case, centered at, we'll make it x equals 5. Or we'll do negative 5. Centered at, well, x or c, we can say for center. And so really we want my r value in a over 1 minus r to be x minus negative 5, right? We want to center it at negative 5. Or to be x plus 5. That's what we want r to be, x minus c. And so in this case, we need to change the way the function looks without changing the function. First, I'll just switch the 2 and the x. And then I will replace x with what I want it to be, x plus 5. But in doing so, I've created a problem, and so I need to make sure I don't change my function. So this would be 2 plus x plus 5. And so now we need a minus 5 here to balance that. That's now going to give me, if I combine the 2 and the negative 5, negative 3 plus x plus 5. So I fixed my r value thing. I've made r what I need it to be, but in doing so, I've created another problem because, again, remember, a over 1 minus r. And so just like I did before, I'm going to divide everything by negative 3 to make that back to a 1. And so we get negative 1/3 here. We get a 1 now, a minus 1/3 x plus 5. And now we're in great shape. We have it in the right form, a over 1 minus r. My r is the right value. I have the 1 here, I have the minus sign. We're happy, and so a is negative 1/3, r is r is 1/3 x plus 5. And we can write this as a power series then. So we get f of x equals n equals 0 to infinity, ar to the n. So negative 1/3, 1/3 x plus 5 to the n. Distributing the nth power so I can bring out that constant gives me negative 1 over 3 to the n plus 1, because 3 to the n and another 3, x plus 5 to the n. And so we have a representation of our function, 2 plus x, as an infinite polynomial centered at negative 5. How long is this approximation good for? Well, this would be good if the value of r which is 1/3 x plus 5, is less than 1. Multiplying both sides by 3 tells me I can move 3 units away from -5. I mean, if you want to think two-sided inequality, we can do this. Subtracting 5 from everything gives me -2 and -8, or 3 units away from -5 on either side. So this is an interval then from -8 to 2. So we have a representation of this function on the interval -8 to 2. That gives me f of x, or gives me 1/2 plus x. All right. Let's just do one more to illustrate this process before we talk about one other thing in this section. So we'll make it a little more complicated here. We'll say f of x equals 3 over 2x plus 3. So 3 over 2x plus 3, and in this case, we'll center it at 1. Centered at c equals 1. We want to find a power series representation, so we want my r to be x minus 1. And so we need to change the way the function looks without changing the function. I'll switch the order. I'll replace x, just x, with x minus 1. The 2 is going to stick there. In doing so, if we think about what I've done, we have a 2x and we have now a minus 2, so I need a plus 2. I'll combine that with the 3 to get 5. I need to make this a 1, so I divide everything by 5. And we get 3/5 over 1 plus 2/5 x minus 1. And we're almost there, but we have to be very careful because the geometric sum formula says a over 1 minus r. And so there's one algebraic manipulation that needs to be done to get it in the right form, and that's just remembering that 2 negatives make a positive. So I'll write that plus as minus minus. And now we have it in the right form. A over 1 minus r. What is a? It's 3/5. What is r? It's negative 2/5 x minus 1. Because of the double negative, so that negative needs to be thrown in with r. And so that means f of x now can be written as this infinite polynomial, centered at 1, 3/5 times negative 2/5 x minus 1 to the n. I'll bring out that negative 2/5. I'll break up that nth power over even the negative sign as well. So I'm going to get this as 3 over 5 to the n plus 1, because I have a 5 and a 5 to the n. Here I have a negative 2 to the n, or a negative 1 to the n times 2 to the n. And that's just to see that's alternating. You don't have to do that. And we get this. So I just distribute that nth power over those terms and combine it with the 3/5 to get that coefficient in front. And so we have a representation now of this function centered at 1. And then the only other thing would be, well, okay, for when, right? For how long is this good, on what interval? And again, that's if the value of r is less than 1. Well, the absolute value doesn't do anything for the negative, or the absolute value, the negative doesn't do anything because of the absolute value. I'll multiply both sides by 5/2, giving me this. 5/2, I mean, think of it as 2.5. So I can move 2.5 units away from 1. If I think of this as a two-sided inequality, I get 5/2 plus 1, so 7/2. And negative 5/2 plus 1, so negative 3/2. So my interval would be negative 1.5 or negative 3/2 to 3.5 or 7/2. So that's the interval on which this is a good representation. So again, we just wrote this function as an infinite polynomial on this interval. And we used a geometric series to do it. Now, of course, in order to use geometric series, if we go back to the other board, we have to remember that my function that I'm given has to look a certain way. Right? It has to be able to be manipulated into a form a over 1 minus r. So you'll notice that all these functions look very similar to each other. They're all kind of rational functions with linear things in the denominator, but we can change it up a little bit. We're going to do a couple things. One is we can also think of maybe 1 over 1 plus x squared, centered at 0. Centered at 0. Well, we just need to do a little algebraic manipulation, the double negative thing. It's already centered at 0. X minus 0 is nothing, so we have a is 1, r is negative x squared. And so we can write this as an infinite series very easily. A is 1, so it doesn't do anything. R, negative x squared to the n. Powers to powers, you multiply. So actually we can write this as negative 1 to the n by pulling out that negative sign, x to the 2n. And so we have a representation of this function. If the value of r, so what? So the value of negative x squared needs to be less than 1. Well, negative doesn't do anything. The value of x squared needs to be less than 1. Taking square roots of both sides, the value of x needs to be less than 1, which gives me the interval negative 1 to 1. So we have a representation of this function on the interval negative 1 to 1. So even if we have that power there. Now where this becomes interesting is, well, what if you're asked to find a representation for arctangent? Now arctangent definitely isn't a rational function like this in which we can use this geometric manipulation or geometric series. And so we wanted a representation for arctangent of x centered at c equals 0. How would we do that? Well, arctangent of x can be written in this way. However, we notice that 1 over 1 plus x squared, I hope you realize, is the derivative of arctangent. And so then, wouldn't the antiderivative of this representation be the representation of arctangent? Right? The antiderivative of 1 over 1 plus x squared is arctangent of x plus c. It's going to be important. And so if we have a representation for 1 over 1 plus x squared centered at 0, then I would get a representation for arctangent by taking the antiderivative of this representation. Now, even though this looks scary to write down, remember that the variable is x, not n. Remember that this is just a polynomial, and it's just a sum. Integrals break up over sums. Polynomial terms, you just use the power rule on, and so that actually means we get x to the 2n plus 1 over 2n plus 1. We add 1 to the exponent, divide by that power. The negative 1 is just a sign, right? So integrals break up, so it's not going to change that. The sum is still from 0 to infinity, right? Because we're not losing anything. We'd have to be careful with derivatives, because when I take derivatives, we lose constants. And so like the derivative of a polynomial, you wouldn't have the constant anymore. So that might change the sum index to now be 1 or something. But antiderivatives we don't, but then we get a plus c, right? Well, I want a representation for arctan, and I need to know then what c is. And so this is equal to arctangent of x. If we want to know what c is, let's just plug in a value and see what happens. Well, we want to plug in a value that we can evaluate. Well, I would plug in the center of the power series. That way we can find what c is. And so I'm going to let x be 0 to find c. If x is 0, we would get the constant term of this polynomial, but you notice there is no constant term. When n is 0, you get x to the 1. So there is no constant term, there's just a linear term. And so actually when x is 0, you get 0 plus c on this side, equals arctangent of 0. If we're good with arctangent of 0 is 0. And so you get C is 0. And so in this case, C is 0, which means arctangent representation can be found using geometric series, but not directly. We would use its derivative representation because its derivative can be written in this way. And therefore get a representation for arctangent. And so what do we have? We have this. Now the question is, okay, well, what about the endpoints? What about -1 to 1? Is it still on the same interval? Does anything change about the interval? Well, let's think about it. I'm only integrating over where it's continuous, so -1 to 1. So definitely the domain should not increase at all. It won't decrease because we are defined in this domain. It is a polynomial. We have continuity in this domain. And so we have it defined here, but the only question would be, what about the endpoints? And that we aren't quite sure what happens when I integrate. And so we do need to check the endpoints. Now, there's no way of getting around that except just plugging it in again, just like we did in the last section. So when x is 1, we get 1 to the 2n plus 1, which means nothing. We get this series here, -1 to the n over 2n plus 1, which is actually a convergent alternating series. All right, so alternating series, by the alternating series test, it converges. And so actually here, we can include 1, where we couldn't have before. What about -1? In this case, we're going to get 0 to infinity, -1 to the n, 2n plus 1. Okay, when I replace x with -1, we get -1 to the 2n plus 1, but notice 2n plus 1 is always odd. It's 1, it's 3, it's 5, 7, 9. And so -1 to an odd power is always just -1. So in fact, it doesn't alternate. It's just times -1. And so this is actually still an alternating series. This is still an alternating series. And that -1 really doesn't do anything. And again, by the alternating series test, it converges. And so again, -1 we can include. So the only thing that changed was parentheses to brackets. You could use the same technique to get a representation for ln of x. And that's because, again, the derivative of ln of x is 1 over x. And 1 over x can be manipulated in this way. And so if we write a representation for 1 over x centered at a certain point, we can take an antiderivative, right? We can take an antiderivative to then get a representation for ln of x centered at a certain point, where, of course, then we would need to check endpoints. And so the last thing I want to just say is just a little bit with calculus and power series, because it came up here. And that's really, what is the derivative of power series? In terms of x. Now, power series, remember this is just a polynomial, so I'm just using my power rule. I bring the n down, x minus c to the n minus 1. But the only difference with derivatives is now my sum starts at 1. This is important. Why? Because now that constant term is gone, and so my linear term becomes my constant term, and so we've lost something, right? The sum starts at 1 to infinity now, where our new constant term is the old linear term. You notice that this still works out, right? If n is 1, we get a1 times 1, which is a1, x minus c to the 1, minus 1, which is 0. And so this term's gone, and you're left with a1, the new constant term, which is what it should be. And so when we take derivatives, we lose constants, so that's why the index changed to 1 now. And then, of course, if we take antiderivatives, we don't lose constants. In fact, we gain a constant, right? So using my power rule in reverse, and then plus c. Typically, you'll see the plus c written on the other side of the sum, and that's just to not confuse us with thinking that c is inside the sum. C is not. So you should maybe write c plus that sum. And this is just the antiderivative, right? My power rule in reverse, because remember that power series are just polynomials. So at any moment in time, it also may be useful to take derivatives or antiderivatives, like in this case, more extensive example, finding a representation for arctangent centered at 0. And so I hope that was helpful, and that kind of wraps up our time in series. And so we're actually going to stop here. We're done talking about power series, testing series, and series is kind of done. And what remains to do is we're going to move into chapter 10, and we're going to discuss another side of calculus, which is going to be what we call parametric equations and curves. So we're going to start a new chapter, which is another change of gear. We're moving out of sequences and series now and moving back to functions and derivatives and graphing things as we know calculus to be up until chapter 9. And so that will be the next video.